Welcome to Chapter 24 on Responsible AI, Interpretability, and Causal Thinking. Here we ask not only whether a model is accurate, but whether it is fair, understandable, and right to deploy. In 2018, a large technology company quietly shut down an experimental hiring tool. That small story captures the theme of this chapter, the wider responsibility that comes with building models that affect people. By the end of this chapter, you should be able to explain why responsible AI matters and why accuracy alone is incomplete. Identify the main sources of bias in a pipeline. See why removing a sensitive feature does not remove unfairness, and describe several group fairness metrics that can conflict. You should also be able to distinguish interpretability from explainability. Use tools like feature importance, partial dependence, SHAP, and LIME, separate correlation from causation, and describe how A/B testing and uplift modeling support causal reasoning. This figure shows SHAP values for a single loan application. Positive bars push the prediction toward approval, negative bars toward rejection. Here, income and credit score matter most, and the chart explains exactly why this applicant got the outcome they did. Earlier chapters chase metrics, accuracy, precision, recall, F1, RMSE, AUC, but a model can score beautifully and still cause harm. A hiring model might downgrade qualified candidates from one group, and a lending model might quietly reproduce decades of past discrimination. A medical model trained mostly on one population can underperform on patients it rarely saw. A recommender can amplify outrage to boost engagement, and facial recognition can be far less accurate for some groups. Responsible AI is the discipline of asking the questions metrics do not. Let us start with bias. In everyday speech, bias simply means prejudice, but in machine learning, it has a more precise meaning. In machine learning, bias is a systematic error that produces consistently distorted or unfair outcomes, often because the training data or labels reflect existing inequalities rather than ground truth. Bias enters through several doors: historical bias from unfair past decisions, sampling bias from unrepresentative data, labeling bias when targets encode prejudice, measurement bias across groups, proxy bias from neutral looking stand ins, and deployment bias from misuse. The hiring tool from our opening story was a case of historical and labeling bias working together, each one reinforcing the other. Sampling bias arises when the training data is simply not representative of the setting where the model will actually be used. Labeling bias is subtler and more dangerous because here the target itself is contaminated by human or institutional prejudice. Now, here is the trap that catches even well intentioned teams: proxy variables, where a seemingly neutral feature secretly stands in for a sensitive one. Fairness sounds like it should have a clean definition, but ask, do groups get similar error rates? Are mistakes concentrated in one group? Does the model deny deserved opportunities? Does it widen inequality? And can a person understand and challenge a decision? These questions overlap, but they do not reduce to a single number. Fairness has many faces. To make fairness measurable, we compare model behavior across groups. For a loan model, we might check whether approval rates and error rates are comparable across demographic groups. In practice, a fairness audit is a loop: measure, compare, and if disparity is too large, mitigate. This figure pictures a fairness audit as an iterative loop. Metrics are computed and compared per protected group, and if the disparity is unacceptable, the team mitigates and re-audits. Only an acceptable result proceeds onward. The claim that fairness metrics can mathematically conflict is easy to wave away until you see it in numbers. Consider a model that is equally good at detecting repayers in both groups, yet still ends up looking unfair. These confusion matrix counts use the same true positive rate of 0.8 and false positive rate of 0.2 for both groups. yet their different base rates produce very different numbers of false positives. Now read three fairness measures off the table. Equalized odds is satisfied with equal true positive and false positive rates, but demographic parity is violated, 0.50 versus 0.32, and predictive parity is violated too, 0.80 versus 0.50. This figure scores the same model on four measures for two groups with different base rates. Recall and false positive rate are equal, so equalized odds holds, yet the selection rate and precision diverge, breaking the other two criteria. This conflict is not a bug we could engineer away. When base rates differ, it is forced by arithmetic itself. It is worth dwelling on accuracy, the most seductive metric because it lies most easily. A high overall accuracy can hide complete failure on a subgroup that the majority simply outvotes. When a model affects a person's life, the answer, trust me, it works, is not acceptable. People deserve to understand the decisions made about them. Interpretability is the degree to which a human can understand a model's mechanics directly. Explainability refers to techniques that explain decisions after the fact, even when the model itself is too complex to read. Some models are interpretable by their very nature, like a short decision tree or a linear model whose weights you can read straight off. Explanations answer two different questions. How does the model behave overall, and why did it make this one particular prediction? The most common global explanation is feature importance, a ranking of how much each feature contributes to predictions. But it is easy to overread, so we treat it with care. If feature importance tells you which features matter, a partial dependence plot shows how one of them matters. The honest caveat is that it can mislead when features are correlated, since the averaging asks the model about combinations that never occur in reality. SHAP, short for Shapley additive explanations, is the most widely used explanation method today, resting on an elegant idea from cooperative game theory. For a credit model, it might show that a high debt-to-income ratio pushed risk up while a long credit history pulled it back down. This figure presents SHAP as an additive explanation. The explainer takes a trained model and one input, then splits the distance from a baseline to the prediction into per-feature contributions, some pushing the score up and others pulling it down. LIME, local interpretable model agnostic explanations, takes a different route to the same goal. Because it only ever queries the model's outputs, it is model agnostic, working on a random forest, a neural network, or anything else. Here is the key point. Every tool in this chapter explains the model, not the world. They tell you what drove a prediction, never that the feature causes the outcome. Mistaking model explanation for causal evidence is one of the most common and costly errors in applied machine learning. That key point leads us straight into the second half of the chapter. The classic illustration: ice cream sales and drowning deaths rise and fall together across the year, yet neither causes the other. Two variables are correlated when they tend to move together. One causes another when changing. The first actually produces a change in the second. Correlation can arise without causation, often through a shared third cause. That hidden third variable has a name, a confounder, which influences both the supposed cause and the effect, and manufactures a correlation that is not causal. The shape of the trap is always the same. This figure shows confounding directly. Hot weather causes both ice cream sales and drownings, so the two move together and look correlated, but no causal arrow runs between them. Banning ice cream would save no one. Causal inference is the discipline of estimating real cause and effect relationships while properly accounting for confounders. The cleanest way to defeat confounding is to refuse to let it form, which is exactly what an A/B test does. Group A, the control, sees the current design. Group B, the treatment, sees the new one. Because assignment is random, the groups are, on average, identical in every respect. A/B testing tells you the average effect of a treatment across everyone. Uplift modeling goes further, estimating the change in each individual's outcome caused by the treatment, not just their likelihood of buying. Most machine learning runs on data about people, and people have a right to expect care. The recurring privacy risks include collecting more data than the task needs, using it without meaningful consent, and re identifying individuals from supposedly anonymized records. When a system changes lives, a human must be able to review, override, and contest its decisions. The failure mode is rubber stamp oversight, where a person is nominally in the loop but in practice just approves whatever the model recommends. You cannot govern what you have not written down. A useful model card records the intended purpose, the training data and how it was collected, the features and target, the evaluation metrics, and performance broken down by subgroup. Responsibility does not end at deployment. In many ways, it begins there. The questions never stop, starting with, has the input data distribution shifted away from what the model was trained on? The single most important responsible AI habit is also one of the simplest. Never report a model's performance as one number. This code loops over each group in the data and computes accuracy, precision, and recall separately for each one, so a single headline number can never hide a weak subgroup. In a real audit, this same loop run on thousands of records is what surfaces the gap between a model that works for everyone and one that works only for the majority. Let us make this concrete on a real, widely used benchmark, the adult census income dataset, where the task is to predict whether a person earns more than $50,000 a year. This code loads the adult dataset, deliberately drops sex from the features while keeping it aside as the sensitive attribute, trains a random forest, and prepares to compare how the model treats the two groups. Notice that we drop sex from the features, yet you will almost certainly still see the model select the two groups at very different rates. Proxies in the remaining features carry the information through. This code uses SHAP on the random forest from before. The summary plot gives a global view of each feature's average impact, while the force plot zooms in on why one particular person was predicted to earn more than 50,000. The summary plot ranks features by overall influence and shows the direction of each effect, while the force plot decomposes a single prediction into the features that pushed it up and those that pulled it down. This code analyzes a simple A/B test. It groups the experiment by the control and treatment arms, computes the conversion rate for each, and reports the difference between them. Because the groups were assigned at random, the difference in conversion can be attributed to the treatment itself, rather than to some lurking confounder we never measured. Consider a regional bank that wants a model to predict which applicants are likely to default. Done well, it could extend credit more accurately and inclusively. Done carelessly, it could quietly rebuild old discriminatory patterns behind a veneer of objectivity. The team's workflow weaves this chapter's ideas together. Only then do they evaluate, and they evaluate twice, once overall and once sliced by group, comparing approval rates and error rates. Throughout, they hold one humbling idea: prediction is not justice. The code that follows trains a random forest on the German credit dataset, uses SHAP to identify the most influential features, and checks for disparate approval rates across demographic groups as a first-pass fairness audit. This code loads the German credit dataset, encodes its categorical columns, splits the data, and trains a random forest classifier to predict good versus bad credit. Printing the top SHAP features makes the model's key drivers transparent to auditors and regulators, while comparing approval rates by group surfaces potential disparate impact before the model ever reaches real applicants. This chapter argued that an accurate model is not automatically a good one. We traced bias to its sources, historical, sampling, labeling, measurement, and proxy, and saw why deleting a sensitive feature fails when proxies remain. The thread running through all of it is judgment. For further reading, look to introductory work on responsible AI and ethics, the model cards and datasheets papers on documentation, the line paper on model-agnostic local explanations, and the unified SHAP framework grounded in Shapley values. More foundational reading includes work formalizing fairness through awareness, the equality of opportunity criterion for fair classifiers, an introductory causal inference textbook, and practical guides to A/B testing and online experimentation. That brings us to the end of Chapter 24, where we learned that building machine learning responsibly takes not just accuracy, but fairness, transparency, causal care, and human judgment.